A very good evening to all of you. So today I'll be telling you about the self-control synchronous motor drive using the load commutated inverter. As you know that the synchronous motor is an AC motor. It is going to take an AC supply. So how you are going to feed an AC supply? So by inverter, by a three-phase inverter, you can feed a three-phase supply to the three-phase synchronous motor. And but you want a controlled AC input, and for controlled AC input you need the inverter. So here we have used a load side converter, but this is the inverter. This will act as the inverter. So for inverter we require a DC supply. It means that you will have to convert the fixed supply frequency or fixed amplitude into the DC, and this DC will be fed to the inverter. So here you are going to use two converters. The first one will be the source side converter and the second one will be the load side converter. So here you can see there are three legs of the source side and three legs of the load side, and the switches we have used here are the SCR, or you can go for the GTO also. So for high power application we generally go for the SCR and the GTO. We can also use IGBT and the MOSFET, but the MOSFET and the IGBT will be having limitation in the power applications. So the first source converter will be acting as a rectifier. Obviously, we want a DC. So this should act as a rectifier, and we want the power should flow from the source to the DC side, then DC side to the synchronous motor, and ultimately you will be getting the mechanical power at the shaft. So for that, your source side converter should act as a rectifier. And when this converter will act as a rectifier, when you are going to fire the gate pulses, when you fire the SCRs between 0 to 90 degree. 0 to 90 degree, if you are firing, it means what? Your converter will be acting as a rectifier. And similarly, if you want an inverter, for inverter your firing angle should be 90 to 180 degree. This already we have seen in the power electronic classes, and for rectifier the firing angle is between 0 to 90, and for the inverter it is 90 to 180 degree. So this is the power flow when you want a power flow from the AC side to the mechanical side. But if you want the braking operation, now in the braking operation what is going to happen? Your power flow reverses. It means that then this then this load side converter should act as a rectifier, and this should act as the inverter. Only then you can feed a power to the fixed supply, otherwise not. So this is the thing which you need to remember, that when the power for a motoring operation, this should act as a rectifier and this should act as the inverter. And for the braking operation, that is a regenerative braking operation, where we are feeding power back to the supply, that time this load side converter should act as the inverter, and this should act as the act as the they should act as a rectifier, and they should act as the inverter. So this is all about these self-control synchronous motor. So basically there are two types of mode. The first one is the true synchronous mode, and the second one is the self-control. So true synchronous mode will be basically in the open loop configuration, where externally we are changing the frequency of supply, and ultimately we are changing the rotor speed. Now you know that the rotor speed of the synchronous motor is the rotor speed of the synchronous motor is the synchronous speed only. Fine, because the rotating magnetic field and the rotor will be rotating at the same speed only. This is not an induction motor where rotor will be having a different speed with respect to the magnetic field. So in the true synchronous mode, we are changing the speed externally. So it will be in the open loop configuration, we are not sensing anything. But in the self control one, we are sensing the suppose if the load changes, what is going to happen? Your suppose load changes, or you can say the load increases, then what is going to happen? Your speed will change, and accordingly by using the Hall effect sensors you are going to measure the rotor position, and accordingly that will be fed back to the supply, uh, went back to the converter, and accordingly the switches will be operated, and accordingly your magnetic field will be changed. So this is happening in the self-controlled synchronous motor. I think the detailed form is not given here, but if you want I can still explain. Okay, so now we'll be taking one numerical. So this is the numerical which we are going to take. So basically, it states a synchronous motor is controlled by a load commutated inverter, which in turn is fed from a line commutated converter source voltage. It means that the synchronous motor is going to be operated with the help of two converter. So you will be having a source side converter, and the second one is the load side converter. Now, what the name given as load commutated inverter, it means that the commutation of the switches is done using the load. Now, how it is happening? You see that your inverter is feeding the voltage. Inverter is feeding the voltage, and initially your motor is at zero speed. Fine, your inverter is feeding the voltage. Initially, the motor is at zero speed, so it means there is no chance of any induced EMF. So when there is no induced EMF, it means the voltage across the switch will be V only. Fine. So when the motor starts rotating, fine. So what is going to happen when the motor starts rotating? The induced EMF will appear in front of you, and the voltage across switch will be V minus E. So suppose the speed increases, or when the motor attains a higher speed, so what is going to happen? The E is going to increase, and in that case your switch will be turned off. So this is called the load commutated inverter, because after the load side converter you have connected the synchronous motor as the load. When the synchronous motor starts rotating, the induced EMF coming into the picture, and that is making your switch to turn off. So this was that is why the name given as the load commutated inverter. So now you will be having this 6.6 kilovolt voltage is fed from these 6.6 kilovolt voltage, 50 hertz is there. Load commutated inverter operates at a, this is the voltage which we are feeding it to the synchronous motor. Now the parameter which are given in the problem are line only, so you can convert it into the phase also. So the load commutated inverter operates at a constant firing angle. Now you can see here, because we want to have the motoring operation. So for motoring operation, the first converter will be acting as a rectifier, and second converter will be acting as a inverter. And when the inverter, so for inverter, the firing angle should be between 90 and 180 degrees. So this is the firing angle, that is 140 degree. And when rectifying, and when this load commutated inverter act as a rectifier, when it will act as a rectifier, when you want a braking operation, so that time you will have to keep the alpha L will be equal to 0. So now this is the parameters of the DC side, that is RD will be equal to 0.1 ohm, and this is the main important thing, that the drive operates in the self-control mode. When you are having a self-control mode, just now I have explained that when the load changes, what is going to happen? The rotor speed changes. So when the rotor speed changes, it means that the your voltage should change, because we are operating in the V by F ratio. Means the rotor speed depends upon the frequency. When the rotor speed changes, it means automatically your frequency is going to change, because the converter, or you can say the synchronous motor, is operating in the closed loop configuration. So when there will be a change in the rotor speed, there will be a change in the frequency, and to maintain a constant flux throughout the operation, you have to change the voltage also. So in self-control mode, V by F should be maintained constant. Now the motor having the detail, that is 8 megawatt motor is there, three phase 600 volt. This is 6 pole 50 hertz unity power factor, right? Great. And star connected, obviously, then it means that this will be divided by root 3. then Xs will be equal to 2.8 ohm, Rs will be equal to 0. When Rs will be equal to 0, it means what? That is the copper loss, and the losses will be neglected. So determine the source side converter firing angle for the following. So the first one, that is a motor operation, and the second one, that is the regenerative braking operation. So we'll try to calculate yeah, in this case your power has to be calculated. So how the power has to be calculated? Okay, so we'll be writing the given data first. I think the solution is with me, so I'll be writing the given data. Yeah, so you can see that V will be equal to 6.6 kilovolt is given. Then we have taken the phase voltage and the frequency 50 hertz. Initially we want to have the motoring operation. Now you can see here the motor details are also there. This is the mechanical power, this is the voltage which is there, which we require it to wait on. These are the rated details. Now P will be equal to 6 and frequency will be equal to 50 hertz. So you can easily calculate the synchronous speed, that is Ns will be equals to 120 F by P. 120 into 50 upon 6, that will be 1000 rpm, and this motor is operating at a unity power factor. So cos phi will be equals to 1. So to find the source side converter, so in that case, now first you will have to calculate what, that is the current you will have to calculate. So yesterday I told you that when you have to calculate the current, that time you will have to use which formula? P will be equal to 3 into P will be equal to 3 into V into Is into cos phi. This formula you will have to use. So you can see here directly Is will be calculated. PM is there, cos phi. This is for the rated operation. We want a rated current. So for a rated, because initially don't directly jump into the section which we have to calculate. First try to calculate the rated current, whatever the voltages and everything is given, that you will have to calculate. So Is will be equal to, this will be the 699.82 ampere. So now there is a relation between the DC link and the DC link current and the source, what you can say, DC link current and this side. Let me just I think I will have to go here. Okay, just wait a minute. ah, so there is a relation between this AC link current and this source current. So what is the relation? So I think I think the derivation is there. So you can just write the formula for it. ID will be equal to pi by 6 and pi by root 6 into Is. So simply you can calculate this value. Now for the load commutated inverter. So what is the thing? Load commutated inverter mean that that converter should operate as the inverter. So alpha L will be equals to 140 degree, and so you can simply calculate the phi, because we want to calculate the power, no? So power we have to calculate, and what is the formula of the power? P will be equal to 3 into V into Is into 3 into V into Is into cos phi. You can see here motoring operation at the rated current. Current is rated, that's why we have calculated the current initially for the rated details. And you can see 500 rpm, the speed has reduced. What you can say that when the rated voltage is given, what was the speed? What was the speed? Speed was 1000 rpm. Is it not? It is 1000 rpm. You can see here the speed has reduced. It means that you will have to reduce what? Voltage, because we need to maintain the constant flux. For maintaining the constant flux, you need to change what? For because as speed changes, then frequency changes, and if the frequency changes, it means that the voltage should also change. So you can see here current is the rated current, but the frequency, that is the speed, has changed. So this speed n will be equals to 120 f by p. So they are in the proportional mode only. Directly you can do the ratio and proportion n2 upon n1 into f1, and accordingly you will have to change the voltage also. V by f ratio is to be maintained constant. Now the power developed, you can simply calculate the power now. There is no big deal. there is no big deal in calculating. So now you have got the V2, so you can easily calculate what? You can easily calculate the this voltages, because we need to calculate the voltages. We need to calculate where is that right. So you can see here VDS will be there, VDL will be there, and ID there. ID is there. So when this ID will flow through this inductor, or you can say reactor. Now basically why we are going to use this reactor, it is going to smoothen the ripples, because when you are going to convert AC into DC, so there will be some AC component which we want to reduce it. So for that the reactor has been used. So now VDL will be equals to what? So there is formula for that. There is a formula for that. No need to go for the derivation. Directly we can write VDL will be equals to 3 into under root 6 into pi V2 into cos of alpha L. So you can simply calculate VDL. So now if you can just if you can just apply a KVL, so this plus minus, so I think VDS plus ID into what? ID into RD and minus VDL. So what you are going to get, because we want to obtain this what you can say this VDS. So simply just by applying a KVL in the outer loop, or you can say in the inner loop, so you can calculate the VDS. But our important thing is what we want to find: the firing angle of the source side converter. You are having the converter at the source side as well, so in that case what should be the firing angle? So that we will have to calculate. So again 3 root 6 upon pi into v into cos alpha. Find 3 into v into cos alpha. Just putting all the things, I think you will get the value VDS into, so you put all the things and you will get alpha s will be equal to 66.86.85. So I think the first part we have easily calculated. There is nothing big deal about this. Okay, it can be easily calculated, right. So I think there are no questions for this. Now in the braking operation, what we will have to do in the braking operation, you see the load side converter will be acting as the inverter. So alpha L will be equal to what? Alpha L will be equals to what? Just have it. Alpha L will be equal to 0. For rectification, it is 0. For rectification, it is 0. And again, this is operating at 500 RPM. You see, the braking operation is also done at the reduced speed. Braking operation is also done at the reduced speed. So now 3 VDL will be easily calculated. V2, that will be V2 will be this, because as you know that for 1000 RPM it was around 38 something. For 1000 RPM you can see, for 1000 RPM it was around 38105. But for 500 RPM you have to change the voltage also, because the closed loop operation is going on and the V by F operation is there. So this is again the same thing, that is ID into RD. Nothing big deal, because already we have IDs calculated. So in this way we can calculate the alpha. So you can see the difference. Initially it was below 90 degree when you were operating in the motoring operation. So now it is, you can see, more than 90 degree. So I think this is all about the this problem. I think you should solve the more problems on the, and your concepts will get cleared. Okay, so if you're having any doubt, please contact me or call me.